Welcome everybody to our talk on learning to validate the predictions of black box classifiers on unseen data. I'm Sebastian and this is joint work with Tamo and Felix. So our work is in the area of machine learning, and in academia, machine learning is situated in a quite simple setup. So we have some data, usually the data is already in a numeric format. It's typically high dimensional vectors, vectors in some high dimensional space. And then we have a problem like learning a classifier on a labeled version of that data. For that we train a model, and then we have this model and can derive predictions from it. Well, but our focus is actually on the setup of bringing machine learning into production, like building real world applications based on machine learning. And in this setup, the actual learning part is very, very small. It's situated by this gray box here. And there's a couple of adjacent data management problems that have to be solved and that are getting more and more attention over the last years. So there's many problems related to the actual training of the models. For example, you need to collect the data. You probably need to integrate data from different data sources. You need to somehow convert the raw, often relational data into features, into a matrix that you can feed into your model. But there's also a lot of problems related to deploying and operating models in production. And in this work, we focus on these blue boxes here, the problem of monitoring machine learning and models in production. So can we rely on their predictions? And also on the problem of data validation. So we have to feed these machine learning models with new data, and there are many problems that can occur in this space. In particular, many of these problems originate from a basic assumption that most machine learning models are built on, which is the so-called IID assumption, which states that the training data on which the model is learned and the serving data on which the model is applied later on to derive predictions come from the same distribution. Now, if this assumption is violated, maybe because there are errors in the serving data that you feed to the model, then in general, we lose all guarantees about the prediction quality of the model that we trained. And these errors can be introduced in quite subtle ways. So for example, it could be that an engineer refactors the pre-processing code that sends data to the serving data to the deployed model. And maybe the engineer accidentally changes the scale of an attribute that was recorded in milliseconds to seconds. So now everything is smaller by a factor of 1,000. And that can already be enough that we cannot rely on the predictions of that model anymore. And in practice, this problem even becomes harder because we might have to operate in scenarios where we don't know the exact intrinsics of the model and maybe not even the feature space. For example, if the model is trained and hosted in a cloud machine learning service. And in most cases, the end user is also not a machine learning expert who is trained to debug and inspect the predictions. In most cases, this end user might be a DevOps engineer. There is some existing work on that already, especially from the machine learning community. But usually this work requires, on the one hand, assumptions about the shape of the changes in the data. So how did the distribution of the data change? And also, it also requires a knowledge of the actual feature space of the model. So we have to know how the numeric data looks like that the model is working on. If you just work with the relational data that is fed to the model and somehow turned into features, then many of these approaches are not applicable. Then there's other approaches from the database community, like for example, the TensorFlow data validation library. And they take a different approach where you define a schema for the feature data and you define constraints for this data. And these are checked before you feed the data into the model. And this requires the person who maintains the schema and writes these constraints to be an expert user that really understands the model and the data and their interplay. And all of these requirements make the practical application of machine learning models very, very difficult. So the goal of our paper is to find ways to automate the validation of the serving data for black box models, where we don't know how the model works internally, where we don't know the feature space, and without requiring distributional assumptions about the shift, and also without requiring expert users. And my colleague Tamo is now going to go into detail how that actually works.
Thanks, Sebastian. So let me walk you through the core idea of our work using the figure on the right-hand side here. Remember that our goal is to predict the performance of a black box model for a given unlabeled data set that may potentially be corrupted. And what we see in the figure now is the usual machine learning process. We have a labeled training data set provided to the black box model for training and estimate the model performance based on a test or validation split of the data. Next, we generate shifted or corrupted versions of the training data. Ideally, we have a domain expert that has some insight into how the data might be corrupted. But what we propose as a default are a set of standard corruptions, such as missing values, swap columns, or adversarial attacks. And then we feed these corrupted data sets to our black box model, not for training this time, but only to generate predictions. And because the corrupted data is derived from the original training data set, we do have labels for it, and we can obtain performance estimates for each of the corrupted data sets. So precision or F1 score or whatever you're interested in. At the same time, we also compute a featureization of the model output for each of the data sets. For the classification case, we adopt an idea from Zach Lipton et al. And use percentiles of the model's softmax output to get a numerical representation of the model output for each data set. Now, we take, for each of the corrupted data sets, the pair of featureized model output and performance estimate, and use these pairs as features and labels to train a regression model. And we call this model performance predictor because that's what it does. It takes the featureized model output and predicts the performance. So let me quickly recap. We start with a classic machine learning setup. We create corrupted versions of the data sets. We obtain features and performance estimates, and we use these to learn a performance prediction model. Now that we've done this, we are well equipped for a real production setting. And in the production setting, we get a previously unseen serving data set without labels, and we want our black box model to generate predictions for this data. We feed it through the classifier and obtain the featureized output that we use as input to our performance predictor. And now the performance predictor produces an estimate of how well our black box model performs on the production data. And if the performance estimate is low, it indicates potential problems with the data source, and we can use this to create an automated warning or alarm. One important advantage of this method is that it will only indicate a problem if the data is shifted in a way that actually affects the model performance that we care about, and not that it raises an alarm whenever some type of shift occurred in the data. Clearly, our approach rests upon the assumption that the synthetic errors are representative of real-world errors. But if you want to see what happens if this assumption is violated, please have a look at the experiments in our paper. Now I hand over to my colleague Felix, who will present some of the most important empirical results of our study.
Thanks, Tamo. In our experiments, we compared the true prediction performance of a machine learning model under data errors on the serving data to the performance predicted with our proposed approach. And we looked at a variety of data sets and prediction tasks. In this figure here, you can see the absolute error of the accuracy in the classification task on tabular data as well as on computer vision data. And in the majority of cases, we can predict the accuracy under data errors with less than 0.02 absolute error. In these cases, the errors that were used to corrupt the data to train the performance predictor were the same as at test time here. But in our paper, we also show experiments in which the error on the serving data is not known to our performance predictor. And it also works in that case with similar absolute errors. Next, we also compared our approach with two alternatives, and we evaluate the F1 score of detecting a shift of a given size in accuracy with these four different approaches. So the figure on the bottom here, right here, shows the F1 score for a method that uses only univariate statistical tests on the input data between training and serving data, referred to as rel, and two other variants which perform similar tests on the histograms of predicted classes, referred to as BVSE. And all these three competitor methods have lower F1 scores than our performance predictor in this setting. The next results we'd like to highlight are in an AutoML setting. So here a user just brings a data set or a prediction task, and the AutoML system does all the rest. It finds the right featureization, it finds the right model, it tunes the hyperparameters. And when using these models, we find that also on all of these models, the F1 score of the proposed approach is better in the majority of cases than the F1 score of detecting a shift in model performance with all the alternative approaches that we talked about on the last slide. Lastly, let me highlight one example that we ran with the cloud service provider for AutoML. Here we used Google's AutoML service with on data which we perturbed with data errors on the serving data. And on the y-axis here, these are two experiments, and in each plot you see on the y-axis true accuracy on the dataset shift, and on the on the x-axis you see the true accuracy, on the y-axis you see the predicted accuracy with our approach. And as you can see, in most of the cases, our approach predicts the performance of the machine learning model under dataset errors very well. Now, there are a number of related approaches, and we did not compare to all of them. One of the things that our approach is less focused on is spotting which types of data errors or which types of data points are relevant for that drop in performance. And here, this is something that the bottom two examples are much better at than our approach. So to summarize, we presented an approach that helps to automate the validation of black box machine learning models. We apply corruptions to the data and learn a regressor to predict how a change in the statistics of machine learning model outputs affects the metrics of interest. We demonstrate that this works well in practice, even with errors unknown to our system. And nonetheless, our approach rests on the assumption that the errors we apply to the data are representative of errors actually happening in practice. And this is a strong assumption, but we did our best to incorporate all the errors we encountered in several years of building machine learning production systems. So we hope that our open source package will help others too to make their lives as machine learning researchers and practitioners easier. Thanks a lot for your attention.